Okay, now to actually run the code, uh, we go to scenarios and we start by the subplane plane. I'm not going to show you the Vulcanian here. It's the same principle, so you can just check it out from what is written in the user manual. So let's go here, and this is the type of table that you're going to fill. It seems a bit overwhelming maybe, but then you can reload the data, so really it's very comprehensive at least. Let's go through all the values one by one. So run name, let's say that we're gonna try and I don't know, simulate I don't know, an eruption of VI3. Okay, cordon VI3. We specified output name also the same. And now we have to go specify the path to the grid file. So we go to where we were before. So this is our TephraProb folder, main folder. Grids, we did the grid 2500, okay. And that's the path we want to specify. We can also, if we don't want to run it on the grid, we can also just come and choose the points UTM, but let's take this one. So cordon 2500 and cordon 2500.mat, which is why we need to come here. Sorry, cordon 500 slash cordon 2500.utm. Okay, same for the winds. So we want to specify the path to the wind file. Let's take the well, there's less to write here. So cordon 01010 txt output files. Slash txt output files slash. Okay, now we have some parameters to enter regarding the vent. So cordon vent easting. So now you want to enter the vent easting and the vent northing, so UTM coordinates. So 620 and 5509271, for instance. Here, sorry, I need to change, but you want to enter -18 the vent zone, and the altitude, let's say it's 1700 meters. Okay, so now we start these are the main parameters of the eruption. Okay, so the minimum height, it's specified above sea level. Okay, so I don't know, let's just say that we simulate between 5 kilometers and 15 kilometers. So this corresponds to 5 kilometers above the vent. Okay, and 16. Okay, and let's say that we want a mass, so okay, 10 to the, okay, let's do 10 to the 9, 10 to the 11, that doesn't really matter. Okay, and we specify an eruption that lasts between 1 and 6 hours. Okay, and in this case we just gonna say that we don't want to constrain. So this constraint here defines whether you sample the height, the mass as a function of the height or not. So in this case, if you specify 0, the height and the mass are going to be sampled independently. Now we have a few parameters to enter for the wind. So you need to enter the number of wind profiles in your population. So you come here, text output files, and you see that you have 14,608 wind profiles. So this is used if you, for example, want to reduce and just see the impact of just using 5 years of wind, then you would just enter the half of that, and this is really used to define the maximum eruption date that you can sample. So the wind start in our case, well, that corresponds to it. It's good. It's the 1st of January 2001 at midnight. We have 4 wind per day. Okay. This variable here, seasonality, when it is set to 0, it means that it's gonna use all the wind profiles available in the wind population that you downloaded. But we know that the closer we get to the equator, the more seasonality you can have, for example, between wet, rainy and dry seasons. Okay. So in the case of Carl and Kauge, we saw that there was not really much seasonality, but let's pretend that there is one. So for example, let's say yes, and let's say for example that our rainy season, so you say wind start rainy, okay, the rainy season, the beginning is between May and November, okay. So what it's gonna do in this case is, instead of running, for example, if we say that we want to run 1,000 simulation, it's gonna first run 1,000 simulations using wind profiles regardless of the date. Then it's gonna run a second set of simulation taking wind profiles only comprised between May and November, and then a third set comprised between November and May. Okay, so that's gonna triple your computation time. Here I didn't discuss that yet, and I won't show you in details, but if you go to the user manual, you see that in addition to the eruption scenarios that I showed you before, we can specify 2 additional aspects. We can do a wind range scenario, and in this case is, for example, you just set a wind range in which the simulations are going to be performed. Okay, so I remember Chuck Connor used that for a power plant in Armenia, and he wanted only to consider the wind that was going into the direction of the power plants. So then if you want to get the true probability in the end, you're going to have to multiply the probabilities that you get of Tephra accumulations there by the probability of the wind going into this direction. But this is something you might want to do if you want to assess the hazard for critical infrastructures or something like that. And the other thing that you can do is you can fix, for example, an eruption date. And this is useful if you want, for a given witnessed eruption, for example, I don't know, Eyjafjallajökull 2010, you want to assess what would have been the impact of different eruption styles if they had started the same day. Okay, so that's just things you can play with if you find any use for it. So let's go back here. In this case, okay, so if you want to constrain the eruption dates, so to do a fixed date scenario, we just would put 1 here and put the eruption date here. If you want to constrain the wind direction, you would put 1 here, and then you would enter your range in which you're going to simulate it. Okay, and then the second thing, well, here you can also specify the tropopause height, which is a function of latitude, and this is used in the model of the Greater and Bonadonna to calculate the mass eruption rate. Then we have sections where we can enter information about the total grain size distribution. Okay, and I can, well, for example, I can use what was published for Cordon Kauge 2011. So okay, so here we just specify the range of phi classes that we're going to consider. Okay, then in Tephra 2, the total grain size distribution is assumed to be a Gaussian distribution. Okay, so what we want to do is that each run we sample a different total grain size distribution as a function of the median and the standard deviation of the distribution. Okay, so here the median is going to be between -3 and 1 phi, and here the standard deviation is going to be between 2 and 3. Okay, and so big deal about aggregation as usual. So aggregation is a very important factor which we need to consider if we want to truly reproduce the Tephra accumulation. In this case, for probabilistic sampling, what we do is we use the method of, again, Bonadonna 2002. She observed aggregation then in 2010, also in Ayafiyat Lake tool. And so what we say is that a part of particles that are finer than 4 phi are going to fall into aggregates that are comprised between -1 to 4 phi. So that's the assumption. And in this case, this aggregation coefficient is just taking, well, it's just how much of the material that is finer than 4 phi is going to be redistributed into coarser classes. And we consider that particles are removed equally for each bin size that is finer than 4 phi and equally redistributed between -1 to 4 phi. Okay, go check the paper if you want more detail. So here, it specifies that between 30 and 70% of the fine material is going to fall into coarser classes. Okay, so now we go to this set of parameters. The long-lasting variable is a Boolean variable between 0 and 1. And if we go back to our eruption duration here, okay, if we had specified a duration that could go above 6 hours, excuse me, the long-lasting function would split any eruption that lasts for more than 6 hours into 2 bits. Okay, setting that to 0 would just consider 1 eruption and not vary the wind. This one shows lets you decide whether you want the plume height sampled on a uniform or logarithmic distribution. If you want to give more weight to small eruptions than large eruptions, you want to adopt the logarithmic approach. Number of runs, okay, so here is just on my Mac, so single computer, so I'm just gonna put 25 runs, okay, just to show you. But you might want to consider more when you run really your probabilistic hazard assessment. And here, these sets of parameters here let you define whether you want to write the configuration files that are necessary to run the model or not. One thing I forgot to specify is this bit doesn't run the model yet. It's just to test your eruption source parameters. So if you just want to test quickly your eruption source parameters, see if you're happy with it, you don't need to write the configuration file, grain size, figures for everything, etc., etc. So by not writing them, you're just gonna save space on your hard drive and make the computation faster. So in this case, let's not write them because we just want to do some tests before running the model. And okay, we want to just write the final figures, we want to write the final log. And this is the par variable is a function that if you use the code on your single CPU computer, you might have multi-cores, okay? And if you have multi-cores in MATLAB, you might have the parallel computing toolbox, which you can just see whether or not you have this icon here, okay? And if you do, it means that you have the parallel toolbox, in which case you can set 1 here, and here you enter the number of cores that you machine have, and it's going to just parallelize the calculation within MATLAB, and it's going to make it a bit faster. And then in the end, So this is a bit tricky. It's sets of empirical parameters that are really depending on Tephra2, and usually you obtain these parameters by inverting your field data. In this case, I have a diffusion coefficient of that. So these are the inversions that we did for the 2011 Cordon-Cauchy eruption. Then you have the lithic density, pumice density that you can check the way you want. So sorry, I forgot to say that this full-time threshold is acting at a limit as a threshold between the two diffusion laws that are considered in TephraProb. Then go to Bernardin et al. 2005 to have more detail on that. Cullen step and particle steps are the integration steps over the column and the particle grain size distribution. So believe that if your calculations are a bit slow, you can reduce this number, which you can lose precision. And then alpha and beta control the mass distribution in your plume. Okay, so if you put both equals to 1 is the same as having a uniform distribution, and in the case of Cordon-Cauchy, the best fit that we had was that. Okay, so that was really a lot of parameters to enter. You should think through before doing that, and let's see what it gives. So what you see is that it's first creating it first goes through the season all, so that's all the wind profiles. Then it goes through the rainy season, resample the eruption source parameters, and then it goes through the dry season. Okay, and so here what you see also is that a total of 25 sampling attempts were performed to achieve 25 sets of eruption source parameters, which is normal because this is the test whether we see if, because in this case we have sampled plume height and mass independently, so the solution was found at every run. So if we go to our TephraProb folder, now we can go into the runs section, and sorry, I still have some old things, so let me just move that here. Okay, and what we did is we just created this Cordon VI3, and this is our first sampling attempt. Okay, meaning that if you run a second set of sampling with the same name, it's going to create a second folder. So by doing so, you can just do as many tests and still preserve what you did before, and you don't destroy anything. So, okay, next step is to look at the output types that you get here. Okay, so I want to quickly show you the structure of the output of each of these runs that you can do. So first, this file here, the mat file, is where all the information about your run is stored. Okay, then we have this conf folder, which is a folder for configuration files, which in this case we haven't written, remember, but they would be populated in these three folders. All, so configuration file using all the wind population, using the wind population in the dry season and the wind population in the rainy season. Okay, if you had selected the seasonality to 0, then you wouldn't get these dry and rainy folders. Then curves is just temporary storage for hazard curves that's going to come later. Figures, so here in these figure folders you can find the sampling of all your eruption source parameters. So for example, aggregation coefficient, how it's been sampled, starting date, duration, mass per run, mass per simulation, median grain size, mass eruption rates, plume height and standard deviation of the total grain size distribution. Then again, we haven't written these files, but this is the grain size file, okay, which we input also to TephraProb. Then we have some log. You can, if you check on the manual, you see that you can write several type of log, but this is the most general one, which gives you volcano parameter, eruption parameters, grain size distribution, and then, for example, at each of your run, you see a difference, well, what happened. Then the out folder is going to be the result of your TephraProb simulations that we haven't calculated yet. Prob is going to be your probability calculation. And sum is the sum, for example, if you have long-lasting eruption, it's going to be the sum of the contribution of each 6 Howard bits. Okay? And then finally, there's this one file which is empty because we haven't decided to run the model, so I will show you that later. So now I would like to show you again, so let's go back to our subplinian scenarios, okay? And from here, since you have run already one simulation, you can come here, load it, you come to your run, here and here, and you can select this math file and it's gonna get your parameters back, okay? So now let's just see what happens when we do this constrain option, which is gonna really sample your mass from your plume height, your wind, and your duration. So let's try and hit OK and see what happens. Again, it's going first through all season, then it's okay. So here first, what we can see is that now the code, at least for getting wind profiles from the entire population, it shows that 31 sampling attempts were performed to achieve 25 sets of eruption scenarios. So that means that in 6 cases, the combination of heights, wind, and duration resulted into a mass that was outside of the initial boundary. Okay, so it means that in this case 6 were out, in this case 8 were out. Excuse me. So now if we go to our output folder, as I said, we see that there is a second one that was created with the same name. Okay, and so we don't destroy anything. So what I suggest now is we redo the same. We come here, scenario, we load our file, okay, we load it, constrain, etc. And then in this case, we're gonna go for write configuration file. We want to write the grain size files, which are the 2 things that are necessary for the model, okay, to run the model. Let's do that, okay. Okay, so let's go to our output folder. So it's the 3rd one. Okay, and now this file t2store.txt, in fact, it contains all the comments that can be sent to TephraProb. Okay, so it shows you that you have, in each line you specify where the model is, which is in the folder model TephraProb, where your configuration file is, where your grid file is, where your text file is, your win file is, where your grain size distribution file is, and where it's gonna write the output. Okay, so if you don't want to run TephraProb on your own computer and you want to send it to a cluster of computer, that's the file you should read to send the comments. But now this one run, okay, eruptions scenario is ready to run. So what I do is I come to scenario, and now I go to run Tephra2. I come choose my run, which is this one, the 3. I take the mat file, and here it first tests the compilation of Tephra2, and then it runs the different, well, each of the separate instance of the model. Okay, you can see the plume height varying at each of simulation, as well as the mass. You can see the input text files, and so here, since we have the seasonality option enabled, it runs 3 times 25 runs. Okay, so that was on a single CPU. Okay, and now in our output folder, if we go to the out, now we can see that these are populated by the output file of Tephra2, which, if I load, it corresponds to easting, northing of each point, elevation that is set to 0, and the Tephra accumulation in kilogram per square meter. So the next step is going to convert that into probabilities of exceeding accumulations of Tephra. Just before going into really the probability calculations, there are a few other things that I would like to specify from here. So let me just reload the run. Okay. So here I showed you so far how to do eruption range scenarios, meaning that your eruption source parameters are varying as well as the wind conditions. If you would like to do one eruption scenario, so fix a parameter on the plume height, mass, or everything, what you need to do is just put a minimum value equals to a maximum value. Okay, so it's gonna sample, well, it's not gonna sample. And all these small details are all explained in details in the user manual. So you have this section, run parameters, and it gives you all these little tricks. Okay, so for example, maximum plume height, enter minimum height equals to maximum height for one eruption scenario, this kind of thing. So be sure you're familiar with these without going much further. And the other thing I would like to show is, for example, a long-lasting eruption. Okay, so this Cordon Cage is good because there was this long-lasting eruption in 2011, and so for example, let's say Cordon 2011. So I'm redoing a new run in this case. This remains the same. Okay. And so we know that there was a plume height between 10,000 meters and 14,000 meters above sea level, and a mass between 3.5 E11 to 5.5 E11. And a duration in house between 24 and 30 hours for the most vigorous phase, in fact. Okay, so let's keep that constraint, and then what we want to specify here is a long lasting equals to 1. Okay, so at each of the different steps, well, the different 6 house bit, it's gonna split the eruption in 6 house bits, within which eruption source parameters are assumed to be constant. So let me go run that. So that's gonna take slightly more time. So see already here, 78 samplings attempt were performed to achieve 25 possible sets of eruption source parameters. While this is being done, let's go see the outputs of what it looks like. And so this is the code in 2011 here. And what I wanted to show you is, for example, now within the configuration folder, you can see that for the first eruption, I have 5 eruption scenarios, okay? So you see already that the eruption has been split into different bits. The other thing I would like to show you is in the figures. So in the figures you have 2 masses, okay? So you have mass per simulation and mass per run, okay? And so if I go for the mass per run, you see I have 25 occurrences. So this is the mass as the sum of the contribution of the 6 house bit, okay? But if you go to the total mass per simulation, you see that you have 125 occurrences. So this is a histogram showing the mass of separate 6 house bits, okay? And okay, so let's see if it has finished. It has. So I'm just gonna go run this one, and I'll let that run, and once that is finished, we're gonna do the probability calculations.